So if we were to put this whole equation into matrix form, we'll have a matrix, we'll have a vector of f of n is equal to the coefficient matrix W times nk minus nk actually, it's just a notation, times vector of c to the k. Now we're gonna write this. F the n is f of 0, f of 1, 2, 3 is equal to this is going to be the first term here. So notice this w to the 0, 0 turns out to be 1. And the next term, w right here is also 1. And yeah, w to the n, w to the 0, and w to the 0. Also for the first column, all the w's are to the 0 power. So we'll have 4x4 matrix right here since we took 4 samples. 1, 1, 1, 1, 1, 1. This shows why we used summation starting from 0, because by doing that we have the first column and first row of this matrix to be 1. It's easier to compute that way. Now the rest is filled in from the matrix right here, w to the negative 1, but w to the negative 2. I'll just copy it to this column right here. Now this matrix, 4x4 matrix, is the coefficient from the CK, the real Fourier coefficient. So now we have this C0, K is from 0 to 3, C1, C2, C3. So now here, these are the unknowns in the equation. So and these are the knowns. Once again, because we measured these values at the discrete points, that's why we know it. And this we call W is equal to e to the negative I 2 pi over n. So when we took our samples, we know how many samples we took, and we know we could consequently know these values. So for example, we have e to the negative 1, we just have when n is equal to 4, have e to the negative I 2 pi over 4 all raised to the power of negative 1. So this right here is just a number, a complex number, and this right here, every single one of them is a complex number. So we can, the purpose of doing it in matrix, so we can find the inverse of this matrix. So we have, if we're going to solve that equation right here, we would have, let me just copy it down. We just call this matrix W. Matrix W times CK So we're looking for C. We can times the inverse matrix on both sides of this. Raised to the power 1. So now, this goes to identity matrix, which times that is just C to the K. So we have C sub K is equal to the inverse matrix of W times the discrete function. Now here, this is the coefficient for a discrete Fourier transform. So if we look at it, we have to find the inverse of this matrix. But it turns out very nicely, we can do it by hand, but it's going to take a while. If you put it in the calculator, since we know all the values, it turns out to be 1, 1, 1, 1, 1, 1, 1. Just negate every term, every exponent. Inverse. So this is the inverse. So if we were multiplying this to f, the actual function right here, I ran out of space. Pause.